So in this lecture on dry etching, we are going to get ourselves introduced to plasma. So predominantly we use plasma for all the dry etching that we do, which is followed after the lithography that one does to transfer the pattern to this intermediate layer. So we have this intermediate layer that has the pattern, right, which can be photoresist or electron beam resist. Nonetheless, it's a resist. It's an indirect transfer process. So the soft material is patterned now. So now the idea is to transfer that intermediate pattern onto the substrate, right? So the underlying material beneath the resist. So how do we do that? So we use a dry process, right? So dry process meaning we use plasma in this case. So let's look at what this plasma is and how we generate and what are the properties of this plasma. So as I mentioned, a plasma process is heavily used in microelectronics or in nanofabrication processes. For instance, we use a plasma for chemical vapor deposition, physical vapor deposition. We use it for etching. We use plasma for ion implantation. We use plasma to remove the resist. We also use plasma to clean chambers. So there are multiple applications that this plasma can be used, right, in micro and nano fabrication. So what is plasma? So this is going back to high school physics, that it is another form of matter, but more interestingly it is an ionized gas, right, that contains atoms, electrons, ions, molecules, molecular fractions and electronically excited species. It's not a simple matter, it's a very complex matter. Okay, so it has all these constituents that contribute to this plasma. Okay, so the plasma in general should be neutral. So right, so there are neutral, what we mean by neutral is the charge, the total charge of the the excited species and the neutrals, and all the charge components should be zero. That's what you expect. But you will also have ionization, right? So there are ions present. So what is the ionization rate? And then you also have deionization. So all these processes happens in the bulk. So overall it could accumulate a certain potential, or it can be neutral. But in principle the plasma should be neutral, given both the positive and negative charge particles in the bulk should be equal. Okay, so this is a very simple plasma generator. This is something you must have seen, right? So you have tube lights, so which works the principles of excited plasma. So what you need is two electrodes, right, and you are applying voltage between these two electrodes, right, and you are trying to make the volume of air between these two electrodes to conduct. Right. But in principle you will not be able to make these two electrodes conduct because of the impedance that you have. So how do we reduce the impedance? Is by creating a concealed volume, right, and then reducing the pressure here, right, and also giving some molecules to initiate this process. So basically you need electrons, right? So you need electrons to flow from one terminal to the other terminal. So how do we generate that? So the first electron will be generated from the electrode itself, but it cannot travel the whole distance. So what will happen is whatever gases we have, that should supply additional electrons, right? So those additional electrons will be accelerated. That is the reason why we need a large voltage, will be accelerated to the other end, and during their accelerated propagation, they will collide and then generate more electrons and so on, right? So this is how you completely ionize and create a charge within this concealed volume, and you will have conduction. So that's what you see. There will be a conduction that will happen, and the whole conduction is enabled by generation of this plasma. So let's look at the voltage that is required to create this conduction. Basically what you are trying to do is break down, right, your threshold between the two electrodes, right. So this is the distance d, the two electrodes are separated by, and you are trying to apply a voltage, and also this is under a certain pressure, let's say, okay. So this is a very classic experiment that was done very long time ago to show the importance of pressure and also importance of air gap on the breakdown voltage. So what you will see here, when you look at the pressure variation, your breakdown voltage goes down, and then it becomes minimum at some point, right, to some 300 volts or so, and then it increases again, right. So there is a sweet spot for the breakdown to happen, right, at a very low voltage, right. Of course there is a breakdown happening at different points, but you need really higher voltages, right, when the pressure is low and also the pressure is high, but there is a sweet spot. So what is the origin of this, right, is the question. So there are two mechanisms competing here, right. So in order to make the conduction happen between these two, you need to create enough charges, right. So in this case electrons need to move from one point to the other. So when the pressure is too low, right, then what is happening is you don't have sufficient number of molecules there to generate these electrons, so that it can contribute for conduction. So that is the reason your breakdown voltage is very low, very high, right. But as you increase, right, so you put in more number of molecules, so you add molecules, so your breakdown comes down, right. So you're reducing the breakdown, and at some point it reaches the lowest level, but then you are still adding, right, so more number of molecules. So what is happening is, so now you have large number of molecules that is actually impeding your electron motion. How they are impeding is by scattering, right. So when you have large number of molecules, these molecules are actually scattering the electron flow. So that is the reason why you need to have higher voltage in order to reach the same breakdown level, right. So this is how this we need to understand this Paschen curve, right. So it's not any pressure, any gap would work, right. At a certain gap between the electrodes, we have a sweet spot pressure that will give you lowest voltage for breakdown. So what are all the things we need to generate plasma? We need a power source, of course. There is an external power source, and there is a in particular we need a RF source, right. We also do DC plasma, but primarily people use RF. We'll see that in the next lecture why RF is preferred over DC, and that will create actually a time varying electric field. So that is the reason why we are looking for RF, right. So we generate electrons and ions continuously, right, and they are also lost continuously because electrons and ions can react and then collide, and some subsequent reactions could take place. So we are continuously generating and losing. So in order to sustain a plasma, right, or stabilize a plasma, what we need is the generation rate, right, should keep up with the loss rate, right. You need partially higher generation rate than the loss rate, so that you can sustain. You can have equal rate as well, which will also sustain the plasma. So another important thing is vacuum system, right? As I mentioned, because of the impedance, you may not be able to generate the plasma, or you need huge amount of voltages to generate this plasma in air, right, in atmospheric pressure. So we go to vacuum systems to reduce the impedance, right, and also to stabilize the plasma. So the RF glow discharge in general can be generated by two ways. So the common way is by putting two electrodes, right. So this is called a capacitive coupled system, because this looks like a capacitor, right. So there is an electrode here and the electrode there, right. So the electrode 1 and electrode 2, and in between you have a dielectric, right. So you don't break down the dielectric in a capacitor, but here you try to supply energy, right. So a capacitive coupling is another way. So this is connected to a source, and then this will be grounded, for example. The same thing is true here as well. So you can do this. This is a very simple way of doing capacitive coupling, because you need to give energy to the volume, right. How are we going to do that? By using a capacitive coupling. And the next way is to do inductive coupling, right. So inductive coupling invariably uses a coil. So I have a coil which is wound on top of a bell jar here, right. When I pass a current through this, and this current will create a perpendicular electric field here, right. And that field will make sure whatever molecules sitting inside this jar will be activated. So you are giving energy to these molecules by creating this magnetic field. Okay. So there are two ways to do that. One is capacitive coupling, directly giving electrical power to the system. The other way is by using a coil, where you create a magnetic field, in turn producing a electric current inside the jars that we have, right. And all of this plasma process depends on how electron interacts with the gas molecules inside the volume. So there are multiple things that this electron can do, and these are all the three primary processes that happens inside the plasma. One is dissociation, next is ionization, and the next thing is excitation. So these are all the three processes that will happen if electron encounters a gas molecule. Okay. Let's look at each process one by one, right. First is dissociation. When electron collides with a molecule, right, it will generate a reactive species, right. So it will basically break the bond. That's what is shown here. So you have an electron hitting this molecule AB, and it is going to just create AB, right. It is again free. You can see here. So electron is hitting AB here, right, and A and B are separated, and the electron is out, right. It is not in any way participating or attaching itself to any of this, right. So this will create free radicals, and these free radicals are very important. Okay. So they will have at least one unpaired electrons, and more importantly they are chemically reactive. That is what you want in a plasma. If you want to do etching, you want to make sure that these molecules are reactive. They can react with our substrate, and this actually would increase the chemical reaction, as I mentioned, and this successive collision that this electron is going to have will increase the neutral plasma gas, right. So this whatever species that we generate here, this reactive species, these are all neutral. You see here there is no charge, right. These are all neutral species, and they are chemically reactive. And the next process is ionization. As the name suggests, you are ionizing the molecule. So unlike the earlier case where you only saw dissociation, here electron is going to do something interesting. So what it can do is, it can take away an electron from the molecule and then make it electropositive, right, and it will go out as 2 electrons. You see, now we have gained the electron in the plasma. Okay, so ionizations are very important so that you increase the electron density in the plasma. So you have a free electron and then you have 2 electrons out, right. The other case is also possible, right. So you have an electron coming in and some molecules have a high electron affinity, it can become, right. So E plus B, let's say, will give you B minus, right. So you can attach this electron to this molecule, that will become an electronegative, right. And these ionized gases make up to about 0.01% of the total plasma, right. It might seem very small, but they are very important to the plasma because they give out electron, right. Remember this, electrons are very important in the plasma. They are the one that are dissociating, they are creating ionization, and also they are creating excitation, right. So dissociation is very important step in dry etching that creates reactive species, right. And dissociate and this ionization actually helps you to generate more electrons. And as I mentioned, different gases or different molecules have a varying level of electron affinity. So high electron affinity means it will take all the electrons, right. It will suck all the electrons and it can consume, right. So it can become electronegative later on, right. So one good example is SF6 gas, which has very high electronegativity, and that is the reason why we use these gas in the transformers, right. In the transformer, very high voltage transformers, you constantly lose electrons, right, and they are accelerated as well. If they come and hits, and it's actually causing damage to the exposed material. So by filling SF6 gas, we can prevent this escape of electron from this high voltage transformers and protect the material and life outside this transformer, right. And the another one is CF3Cl is another material, other gas which has very high electronegativity, and this is split, it's not split. So the plasma by taking an electron can generate fluorine gases here, right, which is also very important for generation of reactive species. So next thing is about excitation, right. So excitation is very common in any plasma, and this is the process that gives color, right, glow to the plasma. The reason why we use this process in tube lights is because of this excitation. What we see is excitation, right, light basically. So the electron is here, and then it can excite the electron to a different state, right. It's just an excited state, and then that excited state can be brought back by re-radiation. So what you see here is a free electron is giving energy to this, and then the electron is actually excited to a different level, and then it will radiate back, and when it radiates back, it gives the photon here, right. And this photon is what gives color, right. So this is what basically happens. This is an excited electron here, and this excited electron can give a photon, and then it comes to the ground state, and this is what creates the optical emission, right. When you see a plasma, this is the color, the red color that you see here is a characteristic of a gas, right. Since it is electronic transition, this strongly depends on the shell levels and the electron levels that you have. By looking at the energy difference, right, because from lambda you should be able to calculate the energy difference, you can say what kind of gas is present inside this plasma. So this is also used to probe the plasma, right, what kind of gases are present inside this chamber, so that we can use it for end point detection. That is very important, because when you have a layer to etch, and this is the thickness of the layer, let's say, and this is the substrate, when you are etching the material is removed, right, and then this will create a certain compound A, let's say, right. But then when you hit the substrate, the material is not there, so the amount of A will reduce, right? And how do we know this amount of A is reduced? Is by looking at the color of the plasma, because this A will have its own characteristic emission, right? And based on that emission, we will be able to say that the reduction in the intensity of this particular emission can be related to complete etch through, or the material is already removed or something like that. So that is what we call end point. Based on that, we can stop the process. And there are a lot of secondary reaction that happens as well, because whatever we discussed, that the dissociation, ionization can also reverse. So you can ionize and then create some radicals. You can dissociate and create radicals, but then these radicals can recombine, right? So we should be able to arrest this process, right? So that we can keep all these reaction necessary to do the chemical etch on the substrate. Okay, so we need to look at the chemical etch chemistry particularly, right? What is the forward reaction, what is backward reaction, and how do we arrest the backward reaction in some cases, so that you create enough number of radicals for etching, right? In some cases backward reactions need to be done to create some solid products or gases, whatever you need, but one need to understand the etch chemistry before you change your gas flow or work with your plasma. So since we are talking about these charged particles in plasma that has RF field, they are constantly moving because we are having RF field, right? So the field, the polarity reverses. So that means your electrons are going to be accelerated, and also your ions are going to also get accelerated and decelerated as the polarity change. But the interesting thing here is the electron accelerates very quickly, yeah, compared to ions. So ions are very slow. Just think about the reason for this, right? The obvious reason that you would imagine is the mass of electrons compared to ions are very low, so that they can quickly react to the electric field, right, that you give to this plasma. Unlike ions, which are heavy, so they cannot move really quickly, right? And also the ions have more collisions, right, due to larger cross section, right? The ions are larger as well, so you can get larger collision that slows them down as well. So the two plots below, right, schematic tells you what is the number of electrons present and the energy distribution of these electrons when you have low pressure and high pressure. So when you have high pressure, the electron energy is going to be low, okay, but it is very confined, right? You will not have electrons with very large energy, right? At high pressure you will have low energy electrons, right? But at a low pressure you will have larger energy electrons, but then you will also have very large spread. Okay, so this will help you in understanding what kind of process you want to do, right? On the right side you will see the energy of the electrons with respect to the process, right? We saw electron attachment, right, which generates ionization, right? It will just come and attach, so it can give negative ions, and ionization process, how much energy is required, and for dissociation, how much energy is required. So based on this we can choose the pressure, right? For instance, low pressures are preferred if you want to do, right, dissociation and ionization, but if you just want to do only electron attachment, only high pressure can be used. But you need to have a combination, right? So low pressure and high pressure, one should understand what is actually happening if I change my pressure, right? If you change the pressure, you are actually changing the process of dissociation and the process of ionization. So when you are developing chemistries, you should also look at, if I want to generate more electrons, what should I do, right? Dissociation to do. If I want to increase the etch rate, I should have more radicals, so I need to dissociate more number of these etching gases, right? And if I want to have more number of electrons, I should ionize. How do I do that? So those are all the things that you do by understanding the distribution of electrons, right? And once you have this plasma, you can do a couple of things, right? So here we are talking about etch. You must have already saw this earlier in deposition lecture, that you can also deposit material using plasma, right? So this is the underlying principle, right? So let's look at the deposition first, because probably you're familiar now. So I'm using silane and NO2, right? Now I'm dissociating this silane gas, right? Silane is a gas here, right? By using this electron. So electron comes, hits this silane, and it creates hydrogen gas, and electron goes away, and SiH2. And now I have another electron hitting N2O, right? So this should be N2O, right? So when I do that, nitrogen becomes a gas, and then I get one oxygen radical, and then electron, one electron which is coming out, right? So I don't have any loss of electron. These two are very simple dissociation, okay? And I have now a radical SiH2 and O. So now 3O and 1 SiH2 can give you SiO2 plus steam, H2O2, right? H2O2 is a gas, you can take it out, and this one is a solid, right? And this is non-volatile. So these two are volatile precursors that creates a non-volatile product, and this is how you will engineer your reaction chemistry to reach a non-volatile product if you want to do deposition, right? But now I want to remove material, right? So I want to etch, so I want to remove. So how to do that? In this case, let's say I have an etchant, CF4 and argon, right? So you will quickly notice that argon is used here just to supply electron. Argon is an inert gas, we all know, right? So argon will not react with anything. So argon is an inert gas. The primary purpose of using argon here is to generate more number of electrons, right? Because we know by now we need electrons in order to activate the plasma and sustain the plasma. So whatever electron we generated, that is going to dissociate CF4, CF3 and fluorine gas, right? And this is again dissociation process. So once we get this process done, now we have fluorine, right, which is a gas, and then silicon dioxide, which is a solid here, okay? So this is a solid, so this is all gas, okay? And now four fluorine atoms can react with silicon dioxide and create SiF4, and SiF4 is a gas, okay, and releasing 2 oxygen in that process, okay? So now you have generated a volatile product by using volatile etchant, right? But you have removed a solid, right? So you have converted a solid to a gas, and this is what makes this plasma etch a solid material, okay? So the reaction chemistries are very different, but we are using plasma in both the cases. In one case we start from gas and end up with a solid, but in the other case we start from gas and we react these gases with a solid and remove that solid and make that solid gas, okay? So this is how we convert a solid material to gas or volatile products, which essentially means etching, right? So now we have understood how this plasma is generated and what are all the important parameters in the plasma, particularly dissociation, ionization and excitation. These are all the 3 processes that happens inside the plasma, and all these 3 processes are natural, it will happen, and all these happen for our own advantage, and we can manipulate the ionization or dissociation inside the plasma by controlling the electron density, right? the energy density of these electrons could be controlled, and by controlling this the energy distribution, we could move towards dissociation or move towards ionization. Okay, so all this can be done by controlling your electron density, and also you can control your precursor gas for etch chemistries. In the following lectures, we will look more into the tool configuration and the reaction chemistries as well.